So nitrogen, what they said here, nitrogen 2 contains a triple bond. Okay, so first of all, we need to know nitrogen's molecule look like this is N triple bond and then N. Okay, so that is triple bond for nitrogens. Second point, the triple bond is formed from the overlap of the s orbitals on each nitrogens to form a sigma bond, and the overlap of two sets of p orbitals on the nitrogen atoms to form 2 pi bond. So at this stage you have to know, when we have triple bonds, one is sigma. As I said, sigma is always at least 1 there. So the other two are pi bonds. And we also need to know that for sigma bond, we need to do hybridization. For pi bond, no need to do hybridization. Okay, so after that, these pi bonds are at right angles to each other. So it is actually something like what we discussed before. One of the pi bond is horizontal, another pi bond is vertical, for example. It will be like that. But the thing is, they don't really ask this in exam, so we can just take it in that way. And if you can't imagine, it is still okay when you just imagine, okay, one of the sideway overlapping is between this horizontal and this horizontal. Another sideway overlap to form the pi bond is between this vertical orbital and this vertical orbital. Okay, then they will form something like this, where it is a bit hard to see. Just remember that they are at right angle. Okay, so one is like horizontal, the other two is like vertical. Okay, so we focus on hybridization today. Let's move on to the next page. So on this page, okay, you can see what I mentioned just now, triple bond, right, for nitrogen. Okay, so one of the bond is sigma bond. It is done by this orange color orbital. So we have the head-on overlap over here, and then you can see this is the horizontal p orbital, which is unhybridized actually. So this and this have sideway overlap, you can see at the back and in front. So they label it as pi 2. So this is the second pi bond. The first pi bond is this one. The vertical orbital has sideway overlap with the vertical orbital here. So they overlap up and down. So after that, they will join up to form something that like horizontal up and down. They will join up afterwards. But now you try to imagine the vertical and the horizontal, they are at right angle to each other. So the triple bond form in that way, 1 sigma and 2 pi bond. Okay. Now our main focus, hybridization. Okay, hybridization. So we want to know as clear as possible how is it and how we understand different kind of hybridization. So first point they mentioned here, the p atomic orbitals can also overlap N-on to form sigma bonds. So this is overlap N-on. So the N overlap with the N-on overlap. So it's to form sigma bond. To form sigma bond, they need to do hybridization. This one I mentioned before. To form pi bond, they don't do hybridization. So yeah, in order for them to do this, they first need to become modified in order to gain s orbital character. They say they need to become modified. So for example, let's say I use nitrogen. Okay, I use nitrogen as my example. Okay, nitrogen, we know that it is 1s2, 2s2 and 2p3. Okay, so 1s2, 2s2 and 2p3. So the orbital diagram to here, like this. And after that, we have to determine whether they need to shift any electrons from here to here or not. So we need to determine. Actually, for this case, no need. For this case, no need because it is just nice, They need to form one sigma bond and two pi bond. It's just nice. We have that in this way. This one will form the pi bond. Sorry, this one will form the sigma bond. This one form the pi bond. This one form another pi bond. So that is the triple bond. It's enough already. So we are not going to do like excited state, like absorb energy and go to higher level. No need to do that. So now you can go straight to hybridization. So there are basically two situations, either from ground state to excited state, then hybridization. This is one way. The second way is ground state, straight away hybridization. So it depends on the suitability of the electrons. Okay, so two ways, either follow this way or this way. So for this case, no need to do excited state, straight away hybridization. Okay, now let's see. The orbitals are therefore slightly changed in shapes to make one of the p orbital looks bigger. Okay, so which means what? Initially, the orbital look like this. Initially, before hybridization, the 2s orbital is sphere. The px is like dumbbell, and then dumbbell in this way, and then dumbbell left and right like that. So there are different kind of dumbbell. Okay, so after hybridization, the orbital looks different. So the orbital look like this. Okay, so it look like that with one small and one big. Okay, so this is what we call the hybridized orbital. So this mixing of atomic orbitals are all these. So let's say I label first. These are the atomic orbital, and this is the hybridized orbital. Okay, now let's see the next point. This mixing of atomic orbitals to form covalent bond is called hybridization. So that means the s orbitals is going to hybridize with the p orbitals. So they need to hybridize because they are now having different energy level. 2s lower energy, 2p higher energy. So they need to mix together to form hybridized orbital with the same energy level. Okay, so there are three situations here: Sp3 hybridization, Sp2 hybridization, and Sp hybridization. So there are three. So the first point, mixing the s orbital with 3p orbitals, three of these, is called Sp3 hybridizations. Each orbital has 1/4 s character and 3/4 p character. Okay, so you try to imagine. I know it's like one of the s mixed with three of the p. So at the end, this one still have 1/4 of the character, and then still have and 3/4 of the p character. It's like 1:3. So mixing an s. Okay, before I continue with the second point, so let's think about in what situations they need to do Sp3 hybridization. So I give you a few examples. Sp3 hybridization. So let's say Sp3 is for molecule that have 4 sigma bond. 3 sigma plus one lone pair. 2 sigma plus 2 lone pair. Okay, so these are the example where they do Sp3 hybridization. You can see something. Sp3 means 1s joined with 3p, and 1 and 3 all together 4, so this is 4, this one 3 plus 1 is also 4, this 2 plus 2 is also 4. Okay, so let's say example, 4 sigma bond. Okay, example, CH4 methane. So this one is Sp3. So the carbon here going through Sp3 hybridization because 4 sigma bond. 1, 2, 3, 4. 4 sigma bond. 3 sigma bond and 1 lone pair. Let's say example, 3 sigma bond and 1 lone pair. Okay, so ammonia. H. Okay, so the ammonia will go through Sp3 hybridization. Okay, so ammonia, as you can see, one lone pair here and sigma bond 1, 2, 3. So Sp3 hybridization. Okay, so 2 sigma and 2 lone pair. Let's say example, water. Okay, water, H2O. 2 lone pair. So you can see the oxygen here has 2 lone pair, 1 and 2, and then 2 sigma bond here and here. Okay, so that is 2 lone pair and 2 sigma bond. So this is sigma. So all these are Sp3 hybridization. Okay, now I let you see how's the orbital hybridized. So you just take a look. For example, carbon. Carbon, initially, it is, okay, I write it down here. It is 1s2, 2s2, and 2p2. So 2 here, 2 here, and like this. Okay, so since there is no lone pair, you have to get rid of lone pair here by doing excited state. So the electron have to absorb energy and come here. So from ground state, you have to change it to excited state. This is called ground state. Then you have to change it to excited state. So the 1s2 is not involved. So the hybridization happens after excited state. So now the excited state happen in this way. There is no lone pair, so the electrons absorb energy and come to the last orbital there. Something like this. Okay. Then after excited state, now hybridize. So how they hybridize? If they want to form 4 sigma bond, they need to do Sp3 hybridization. That means the s orbital combine with the p orbitals. So they hybridize in this way. This 1s2 will remain, and then 4 of these hybridize. 1, 2, 3, 4, and then they are going to form sigma bond here, sigma bond here, sigma bond here, and sigma bond here. So all together 4 sigma bond. So you can see the situation in this way. This is methane. So this is methane. Methane go through Sp3 hybridization in this particular way. So methane. So the next one is ammonia. So let's see how ammonia go through the hybridizations in details. So we start from nitrogen. So we know that nitrogen is 1s2, 2s2, and 2p3. So this is the ground state. So do we need to go to excited state or not, actually no need, because this is one lone pair, and these three are ready for 3 sigma bond. So no need to do hybridization. Sorry, no need to come to excited state. You can go to hybridization straight away. Okay, so hybridize. So where the one S2 remain, then 4 of these combine to be lone pair and 3 unpair. So the 3 unpair is going to do sigma bond later. So this is the lone pair. Okay, so you can see it is just perfect. Lone pair and 3 sigma bond. So this is also Sp3 hybridization. Okay, so this is the second situation. And now we look at the third situation. So the third situation is oxygen. So we know oxygen is like 1s2, 2s2, 2p4. So it's like this. And after that, we need to know this is ground state. Then you have to see whether they need to go through excited state or not. Actually no need, because this is just nice. Lone pair, sigma bond, sigma bond. Okay, so they do Sp3 hybridization. So something like this, they hybridize. So the one S2 remain, and then 3 of these combine. So lone pair, and then unpair. So we have the first one, lone pair, then lone pair, and then sigma bond, and it is just nice. Okay, so this is all about Sp3 hybridization. Okay, now let's see the next one. The next one is mixing an S with 2 TWO, 2 p orbitals is called Sp2 hybridization. Okay, so let's understand this. In what situation they have to do Sp2 hybridization? Okay, so I list down all the possible situations. Okay, so Sp2 hybridization, if there are 3 sigma bond, 2 sigma plus 1 lone pair, and I think 1 sigma plus 2 lone pair is like no example. Okay, so now let's see 3 sigma. In what situation they form 3 sigma? Let's say for example Bf3, Bf3. Okay, so first we need to know boron is group 13. So boron, the electronic configuration is 1s2, 2s2, and then 2p1. Okay, something like this. Okay, so this is 1s, 2s, and 2p. This is boron. Okay, let me double check with the periodic table first. For boron, yeah, okay, it's correct. Then again, you need to see this is ground state. So are they going to go through excited state or not? It depends on whether the electron here is suitable to form 3 sigma bond or not. So sigma, sigma, and sigma. Okay, so of course that is not suitable yet. Okay, because there is a lone pair here. So they need to absorb energy and come to higher energy level. So this is called excited state. So they have to go to 1s2, then electrons shifted to the 2p orbital, so this is called excited state. Now they have to do Sp2 hybridization, where one s orbital mixed with 2p orbital, so the 1s2 remain. So what happened is these and these mix up, hybridize in other words, so they will form something like 1, 2, 3, and the last one remain unhybridized and there is no electron there, so this is 1, 2, 3, 3 sigma bond, so they can form 1, 2, 3, 3 sigma bond, as in boron trifluoride. So this is Sp2 hybridization. So it happens to boron trifluoride, 3 sigma bond, no lone pair. So the next one, 2 sigma plus 1 lone pair. 2 sigma plus 1 lone pair. So it is possible also. Okay, it is possible also. Let's say you try to imagine it is like Sp2 means you will get a total of 3, so 2 plus 1 is also 3. Okay, so let's see example for this. Let me check first whether I can find any suitable example for this. Two sigma bond and 1 lone pair. Oh, there is no suitable example here. Okay, so this is a bit rare and I just assume this one is taken in this way straight away. Okay, we go straight to the next one. The next one is mixing an S with 1 P type orbitals form Sp hybridized orbital. Okay, so Sp hybridized means one s orbital hybridized with 1 p orbitals, so 1s and 1 p. So let's see example. So we have Sp3, Sp2. Now let's take Sp. So Sp happens to 2 sigma bond, or 1 sigma plus 1 lone pair. Okay, so 2 sigma bond. Let's see example. 2 sigma bonds, carbon dioxide. Okay, carbon dioxide. Yes.
Eric, just to let you know, I don't think hybridization is on my test.
Oh, okay. Oh.
But it's okay, I can still learn it.
Oh, okay. Yeah,
for next time.
Yeah, I just quickly go through. Okay, quickly go through, then it's almost finished already actually. Yeah, okay. So carbon. One S2, 2S2, and 2P2. Okay, now they have to do hybridizations in this way. Okay, they are ground state now, and you can see carbon dioxide is like this, double bond. So they have 1 sigma bond and 1 pi bond. Then we also know that sigma bond, 2 of them, and pi bond, 2 of them. So this is not suitable because this is lone pair. So they have to go to excited state. Yeah. Okay, so like this. excited state, then they hybridize. Okay, so when they hybridize, you can see these two hybridize. These two unhybridized. So where that two will form 2 sigma bond and these two will form 2 pi bond. Okay, so this is how it works. You can see this is where there is one s orbital combined with one p orbital, so that's why this is called Sp hybridizations. Okay, so let's move on. Okay, so this is where we look at the picture only. The first one, modified p atomic orbitals, example from carbons. This is the, you see one small and one big. Okay, so okay, again, this is the hybridized orbital, as this is one small and one big. This is the s orbital. So after that, this is from hydrogen, this is from carbon. So after that, they form sigma bond between carbon and hydrogens. Okay, so that is the CH bond. CH bond. Okay, CH bond. Initially, they overlap like this. They overlap like this. So the hybridized orbital is here, the s orbital is here. After hybridized, they form molecular orbital that look like this. And this one is p orbital and p orbital. So for example, it is like between carbon and carbon, carbon and carbon. So initially they overlap like this and like this. So after they overlap, now they become like that. Okay, so overlap and become like this. Okay, let's move on. Okay, so this is s orbital and 3p orbital. We have px, py, and pz. So sp3 hybridization. So basically, when they hybridize, they will form 4 hybridized orbital. They will form 4 hybridized orbital, which is like this. So that's why you can see a dot here. A dot here is actually this small circle. Then they come here, one hybridized orbital, another one go up, then one go here, another one go to the back. So they form this shape. This is tetrahedral shapes. Okay, tetrahedral. And next one you can see here, this is Sp2 hybridization, which is 1s combined with 2p. Then the hybridized orbital will look like this, and there are 3 of them. So one go this way, another one go up, and then go this way. So this is what we call a trigonal planar. And next one, the last one, we have one s orbital hybridized with one p orbitals. Then they will form these shapes. Okay, one hybridized orbital go to the left, another one go to the right. So they will form linear shapes. Okay, let's move on. Bond energy and length. Okay, so bond energy and length. Okay, let's see. Covalent bonding, bond energy and length. So what is bond energy? Let's look at this. Is the energy required to break 1 mole of a particular covalent bond in the gaseous state. Okay, so for example, let's say chlorine and chlorine in gaseous state. So the amount of energy required to break this bond is known as bond energy. The unit is kilojoule per mole. The larger the bond energy, the stronger the covalent bond is. Of course, reasonably true because if this is a strong bond, of course you need more energy to break it. Bond length. The bond length is internuclear distance of two covalently bonded atoms. So that means it's like from this nucleus to this nucleus, then you can have the bond length. Okay, so for example, you can see here, single bond, the bond length is 147 picometer. This is 134 for double bond. Triple bond is 120 picometer. So different kind of bond have different bond length. It has different strength also, so this one is long and the amount of energy, this is the bond energy, is lesser, this one more, and this one the most, showing that this is the strongest bond. Okay, strongest bond. So as you can see here, the greater the forces of attraction between electrons and nuclei, the more the atoms are pulled closer to each other. Okay, as in here, greater forces of attraction, they are closer to each other, showing that they are strong. This decreases the bond length of a molecule and increases the strength of the covalent bond. So this is short, but it is strong. Triple bond are the shortest and strongest covalent bond due to the large electron density between the two nuclei of the two atoms. Okay, so which means there are 6 electrons here and the nucleus can attract firmly with the 6 electrons. So imagine here you have the positively charged nucleus, here you have also another positively charged nucleus. Okay, so it's something like this. The positively charged nucleus, 6 electrons in between to form the triple bond, and positively charged nucleus. So the positive and the negative attraction will be very strong over there, as I show in blue color. Strong bond. Okay, so that's why triple bond is very strong, and hence the bond length is short. So these increase the forces of attraction between the electrons and nuclei of the atoms. As a result of this, the atoms are pulled closer together, causing a shorter bond length. So it's short. The increased forces of attraction also means that the covalent bond is stronger. So triple bond is the strongest. That is the conclusion here. Now let's move on. Reactivity of covalent molecules. Okay, let's see here. The reactivity of a covalent bond is greatly influenced by the bond polarity, the bond strength, the bond type. Okay, so what is the bond polarity? For example, let's say HCl. So HCl, because chlorine is more electronegative, the bonding electron is closer to here. So here is hence a bit negative, here is a bit positive. So this is the bond polarity. So where the covalent bond here is polar bond. So if it's polar bond, they are more reactive. If they are non-polar bond, then they are not so reactive. Okay, so this is polar bond, and the result is more reactive. Okay, compared to let's say hydrogen and hydrogen. This is non-polar bond, so not reactive. Okay, now the next one is bond strength. Bond strength also affects the reactivity. So for example, okay, this one, okay, now this one, and triple bond. You know, triple bond is strong, and hence it is N2 is unreactive. Where imagine nitrogen is used in Haber process. To do Haber process, we need high temperature and high pressure. Okay, so showing that it is very hard to break the bond, so that's why we need high temperature to make the reaction works. So the next one, the bond types, sigma or pi bond. Okay, so if they have a sigma bond, the bond is stronger, then it is not so reactive. If they have pi bond, then they are more reactive. So for example, this happens in some organic molecule. Okay, so you can see, for example, methane, sigma bond, so unreactive because sigma bond is strong. And then ethane. So ethane, we have sigma bond and pi bond, so this is reactive. Okay, because pi bond is not that strong, so you can easily break it down and react with other reactants. Okay, so let's see the question here. Work example, bond length and bond energies. Answer the following questions related to the bond length and bond energies of some hydrogen halides. Suggest why the bond energy values decrease in the order HCl, HBr, and Hi. Suggest a value for the bond length in HF. Suggest which hydrogen halide is the most reactive. Okay, so we discussed this straight away. So I will just ask you some questions, then I check whether you understand or not. So if I have HCl, HBr, and Hi. Okay, so first of all, let's think about the size of chlorine, bromine, and iodine. So which one is the biggest? Chlorine, bromine, and iodine.
Is iodine the biggest one?
Yeah, iodine is the biggest in size. Okay, so in terms of size, okay, let me write down first. In terms of size, chlorine is smaller than bromine, and then bromine is smaller than iodine. So iodine is the biggest. Okay, so after that, we think about the bond energy then. Okay, so let's think about the bond length first. Bond length. Okay, so what do you think? Which one has the longest bond length out of these three?
Bond length.
Yeah.
Would it be iodine again?
Yes. This is where Hi has the longest bond length because this is big in size, so making the length here longer. Okay, so in terms of bond length, HCl is smaller than HBr and then smaller than Hi. And because of that, the bond strength, right? Bond strength, you have to know that bond strength decreases when bond length increase. Okay, so when the bond length is increasing, so basically it is easy to break, so that's why the bond strength is decreases. So that is the first part. Now number one, and okay, you can see
So
the
is this only for hydrogen halides?
yes, hydrogen halides work in this way. So for others, you have to consider first the size, then bond length, and then bond strength. So normally we consider in this order.
Okay.
Okay, and at the end, let's see the table before we answer number 2. So you can see HCl, the bond length shorter. This is 0.141, this is moderate, and this is the greatest, 0.161. Okay, so the bond length increases in this way, and then the bond energy decreases. Bond energy decreases, meaning that the bond strength is decreasing also. Bond strength decrease. Okay, so now number 2, suggest a value for the bond length in HF. Okay, so basically, what do you think for HF? Is it a value smaller than this one or greater than this one? What do you think?
Shorter bond.
Yeah, shorter. Okay, should be shorter than 0.127. Okay, so how to suggest, we don't have any fixed value for you to put, so you can just roughly see the trend here. Like this is minus 0.2, minus 0.02, then this one is like around 0.1, 0.014. Okay, let's say I minus 0.014 again, so the value is around 0.013 nanometer. Okay, so I just follow the trend. I see how much to minus, then how much to minus to predict. So sorry, 0.113. Okay, 0.113. Okay, around this, and suggest why hydrogen halide is the most reactive. So of course, why they are the most reactive, suggest which hydrogen halide is the most reactive. So what do you think? HCl, HBr, Hi, which one is the most reactive?
Would it be the one with the lowest bond strength?
Yes, correct. Okay, so Hi.
I.
Yes, that is correct. Okay, so Hi. So of course, why is kind of reasonable because it has the weakest bond, so it can break easily and react with others. Okay, so let's move on. Shapes of molecules. Okay, now let's go through this. The valence Shell's electron pair repulsion theory predict the shapes and bond angles of molecules. Okay, it's based on this theory, VSEPR, to predict the shapes and bond angle. So you need to memorize some values like tetrahedral shapes, 108.5. Okay, so you have to memorize the bond angles at the same time. So electrons are negatively charged and will repel other electrons when close to each other. In a molecule, the bonding pair of electrons will repel other electrons around the central atom facing the molecule to adopt a shape in which these repulsive forces are minimized. Okay, so what they're saying here is, let's say, for example, CH4. So the carbons has bonding electron here, 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 and here. So they have to try to stay as far as possible from each other because the bonding electrons are repelling. So the best way to arrange them is they put in tetrahedral shapes. so that this and this has minimum repulsion, this and this also have minimum repulsion, likewise this and this has minimum repulsion as well. Okay, so tetrahedral shapes is formed at the end and with certain angles. Okay, so where you have to know that for tetrahedral shapes, sorry, the angle should be 109.5, tetrahedral shaped 109.5 degree. So they will form bond angle in that way because they want to have minimum repulsions. Okay, now
then wait, what about the other angle, like between the other hydrogens?
Will be 109.5 also. All this will be 109.5. All these 109.5.
Then wouldn't that be like 430 degrees total?
Yeah, well, we don't take it as a
circle,
flat surface or as a circle because this is a 3D shape. So
okay.
yeah, so that's why you feel like, oh, a total is not 360, because it's not a circle, it's a 3D shape. This is slightly in front, this is slightly to the back, and then so it's a 3D shape. Okay, then now let's see the next one. When determining the shapes and bond angles of a molecule, the following SEPR rules should be considered. Valence shell electrons are those electrons that are found in the outer shell. So we consider valence shell electrons because they are forming the sigma bond and the lone pair. So we are considering them. Electron pairs repel each other as they have similar charges. So why they repel? Because they are all negatively charged, so that's why they repel. So repulsion between multiple and single bonds is treated the same as the repulsion between single bonds. Okay, so single bond, double bond, triple bond, same repulsion based on the information here. Okay, repulsion between, okay, this one I give example. Let's say, let's see. Okay, I put double bond and triple bond. So the repulsion is the same, so that here to here is 180 degree and here to here is also 180 degree, same repulsion. It's not to say like, oh, triple bond bigger repulsion, no. Okay, it make a bigger angle, no. It is same. Double bond, triple bond, same repulsions. Okay, so that's why same angle between this and this.
So what shape would these be called?
This is called linear shaped. Linear. Okay, so this is linear.
Both are linear?
Yeah. Both are linear, and then the bond angle is 180 degree. And then let's see more. Repulsion between pairs of double bonds are greater. Pairs of double bonds. This is pair of double bond. I think I have to give different examples. Let's see whether I have any other examples on pair of double bonds. Okay, I think I have to give let's say SO4 2 minus. This is sulfate. SO4 2 minus. Okay, so let's see how's the electron are arranged over here first. Okay, so you can see double bond with O, double bond with O, and then okay, so I put like this first, before I put the shape, right? So you have to know that two of the oxygen will take negative charge, and then they form single bond. Another two oxygen form double bond. Okay, so 1, 2, 3, 4. Okay, so at the end, sulfate look like this. Sulfate has single bond, double bond, and double bond. Okay, so based on the information here, what they say is repulsion between pairs of double bond are greater. Okay, so that we have greater repulsions over here, greater repulsion compared to here, compared to here. Okay, so single and single less repulsion, double has greater repulsion. So at the end, you may feel like, oh, 1, 2, 3, 4, 4 bonds should form tetrahedral shapes. Okay, should form tetrahedral shape. But the problem is they form tetrahedral shapes with angle which is not same everywhere, you know. So they form something like this. They form something like S. Okay, they form S.
Oh, also like, so is the angle between the double bond and the single bond the same as the single and single?
You mean the angle between single and double? Same as single and single?
Yeah, is it the same?
Not the same. This is the smallest actually. The smallest. Okay, then this is moderate, and then this is the greatest.
Oh, but I thought there was greater repulsion between the double bonds.
Okay, hold on. Okay, yeah, true. Repulsions are greater, so I have to put in this way then. Sorry, this one is misunderstanding here. Okay, so let's say I put the this one is the greatest repulsion, so the angle is in general more than 109.5. Okay, greater repulsion. So here to here is moderate. Okay, moderate. Here to here is the smallest. Okay, so this will be smaller than 109.5.
Okay.
This one is around 109.5. Okay, now let's see the next one. Okay, the next point. The most stable shapes is adopted to minimize the repulsion forces. Okay, so of course they will have a particular shapes. Okay, like tetrahedral for this case. Why? Because they want to minimize the repulsions. Okay, then let's see here. Different types of electron pairs have different repulsive force. So if you have lone pair of electrons, then it have a more concentrated electron charge clouds than bonding pair of electrons. So this is the lone pair, imagine. This is the lone pair and the lone pair. Okay, this is water molecule, right? So here is where we have the bonding pair. This is lone pair. So the repulsion between the lone pair and lone pair is the greatest. So you should expect here to be greater. Should be greater. and here to be smaller. Okay, smaller, and this is the smallest because this is the least repulsion. So at the end, what angle is this for H2O? So we have to know that the bond angle that we talk about will be the bond angle between bonding pair and bonding pair. So we have to say that water has a bond angle of 104.5 degree. The shape of bond angle is band shaped.
Oh wait, so for the angle we only mentioned the one that's between
the bonding electrons.
pair.
Yes. So we are talking about this angle. We are not talking about the bonding pair and the lone pair. The angle here is bigger.
Okay.
We are not talking about that. We are talking about this. So even in exam we write this. And we say it's band shape because we don't care about the lone pair, so consider this alone, that is the band shape, like inverted V. Okay, so it is even written here, HOH angle is 104.5, HOH. Okay, so now let's move on. Okay, molecules can adapt the following shapes and bond angle. So you can see we have linear shapes, so 180 degree, trigonal planar, 120 degree. This is for 3 sigma bond with no lone pair. Okay, so this one is for 2 sigma bond, 0 lone pair. This one is 3 sigma bond and 0 lone pair. This 104.5, 104.5 is the water molecule just now. This is for 2 sigma bond and 2 lone pair. So this is 107, this is for 3 sigma bond plus 1 lone pair. So example is like ammonia. Okay, so this one is H2O.
Wait, for example, like the pyramidal one, why is it the angle between the like A and the X and not the X and the X?
It is actually the X and the X. Okay, so this is an error.
Oh, is it because it's like 3D?
It's actually an error. So it's something like this. Ammonia is like this, right? It's between the HNH. 107 is there. So we don't take this angle. This angle is bigger than 107. So we don't take that.
So
we take this.
For the bent one on the left, is it also wrong as well? Is it meant to be between the X and the X?
Yes, true. This is wrong also. Okay, so for example, water. Oops. Water. H. So the angle is here, 104.5. Okay, and then we have a tetrahedral shape, 109.5. So example is like CH4. Then we have trigonal bipyramidal. Trigonal bipyramidal is where there are 5 sigma bond. 5 sigma bond. Let me write down first. Just now this one is 4 sigma bond, 0 lone pair. This is 5 sigma bond, 0 lone pair. Example is like, for example, Pf5. Pf5 has these shapes, 5 sigma bond. So how to understand this shape is like there are a horizontal triangle where phosphorus is there, and then they extend up and down to form 2 pyramids. So it's something like this, and one more pyramid extend downward. Okay.
Oh, so like, you know the line that's like a black triangle? Is that like it's coming towards me? And then
Yes.
like the dashed line is like away from me?
Yes, correct. Okay.
Okay.
So this is towards our south. So this is here, F, 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 and then one down and then one up. Okay. And then octahedra.
Okay.
Yeah. Octahedra, for example, this is for six sigma bond and 0 lone pair. So example is like sulfur hexafluoride. Okay. So you see over here there are two angles. This one is 120 for the triangle, and then this is 90. But for this case, all of the bond angle are 90 degree. So we have a square horizontal plane, and then they form pyramid up and down. Yeah. So can imagine this one, something like this.
So is it like just now, but like a square?
Yes. Yeah, so it's something like that. So they form pyramid up and down, like this. Okay, it's a octahedral we call it. Okay. So when you draw, you put the sulfur in the middle, and then you put the fluorine up, down, and 4 of them here. Then the bond, 1, 2, 3, 4, 5, 6. Okay, so we have done for this. Now let's see example. Okay, so here we have the boron trifluoride. Okay, so this is 3 sigma bond, so you have to know that 3 sigma bond, no lone pair. So the shape is trigonal planar. The bond angle is 120 degree. Okay, and then this is the next one, carbon dioxide, it's double bond. Okay, so after that they said is similar to single bond. So this is 180 degree. Okay, 180 degree. And okay, compare between these. This is 3 sigma bond, 0 lone pair. This is 2 sigma bond and 0 lone pair. Okay, so linear shapes. Now let's look at this. The next one, CH4, methane. So methane is tetrahedral shapes, 109.5. So this is 4 sigma bond and 0 lone pair. And this is the next one. This is ammonia, 107. So the bond angle is here, 107 degree. So the lone pair and the bonding pair has greater repulsion, making here smaller. So this is 3 sigma bond and 1 lone pair. So remember, this is pyramidal shapes. Okay, as you can see here, pyramidal shapes. So let's move on. This one is H2O. So H2O is 2 lone pair and 2 bonding pair. So I prefer to put it in this way, 2 lone pair and 2 bonding pair. So making the angle here to be smaller, 104.5.
So in the exam, would they ask us to like draw it as like a diagram as well?
Yes, you have to draw something like this.
So for the lone pair, would I draw like the 2 dots like you, or do I draw like an egg?
It's up to you actually. So
okay,
both will be acceptable. So you can even add something like this. Okay, it's acceptable as well. Okay, then this is octahedral shapes. So the dot and cross diagram look like this, and then the octahedral shape look like this. Okay, so you can see 6 sigma bond. So this is 2 sigma plus 2 lone pair. This is 6 sigma bond, 0 lone pair. Okay, now let's move on. So the next one is Phosphorus Pentathlorite Pf5. So Pf5, the shape is trigonal bipyramidal. So it's a triangle, and then one up and one down. So we have bond angle 120 degree and 90 degree. Okay, so 5 sigma bond, 5 sigma bond, and 0 lone pair. Okay, now example. Okay, so it's your turn to try. I wait for your answer. Okay, so for the first one, PCl5, it is P in the middle, then like this, then like that, and then Cl, 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 and then Cl, Cl. So this shape is called trigonal bipyramidal. Okay, number 2. So it is nitrogen in the middle, lone pair, and then like this, like that, and then like that. So the CH3, right? CH3, CH3. For the one on the left, right? So you put H3C. Make sure the bond is linked to carbon. Okay, so this is pyramidal shapes. And number 3, C, and then like this, and then dotted, and then like that, and then Cl, 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 and Cl. Tetrahedral shapes. Okay, so like this. Can or not for the shapes here? Okay, now let's move on.
Yeah.
Okay, so this is the blank page actually for us to draw. And now let's see hydrogen bonding. Okay, so let's go through. Hydrogen bonding is the strongest form of intermolecular bonding. Okay, so that means we have the van der Waals forces and hydrogen bond. Hydrogen bond is the stronger one. So that's why when you compare between intermolecular bonding, this is the strongest. Okay, but of course, if you compare with ionic and covalent, so ionic and covalent is stronger than hydrogen bonding. Okay, so yeah. Intermolecular bonds are bonds between molecules. Hydrogen bonding is a type of permanent dipole bonding. Okay, so permanent dipole and permanent dipole is actually what? So for example, let's say you have water. Okay, let's say H2O and H2O again. Okay, so you know this molecule are polar. So where here is delta negative, here is delta positive. Delta negative. Okay, so the hydrogen bond is formed here between the lone pair of oxygen and hydrogens. So we call it permanent dipole because the delta negative here is always delta negative. In 24 hours it is delta negative. So the delta positive is also permanent. It's 24-hour delta positive. So it is called permanent dipole bonding. Okay, so hydrogen bond is here. Now for hydrogen bonding to take place, the following is needed. A species which has an oxygen or nitrogen, which is very electronegative atom with an available lone pair of electrons. So I have to say it's not just O or N, it also includes F. Okay, so O or N or F. You know, F is the most electronegative element, so they can form hydrogen bond as well. Okay, so you have to make sure there is lone pair available. For example, like this, it has lone pair available, then they can form hydrogen bond with another species with an OH or NH group, or even HF group. HF also can. HF. So meaning that the hydrogen here must stick to FON. Must stick to FON. So if the hydrogen stick to FON, like here, they stick to FON, they form covalent bond with FON, then this hydrogen can form hydrogen bond with the FON of another molecule. Okay, so the idea is like that. So let's say in what situation they cannot form hydrogen bond. Let's say, for example, so I put C, H, 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 and H. Okay, so this one is not hydrogen bond because the hydrogen is not stick to FON, it stick to carbon, so it's not positive enough to form hydrogen bond. Okay, so it's not hydrogen bond for this case, but this one, yes, this is hydrogen bond. So it is always FON and hydrogen that are involved in hydrogen bonding.
Okay, but the hydrogen has to be bonded to either FO or N, right?
Yes, correct. So if it's bonded to C, then cannot, not qualified. Okay. So when hydrogen is covalently bonded to an electronegative atom such as oxygen or nitrogen or fluorine, the bond becomes very highly polarized. That means it becomes very positive. The hydrogen becomes so delta positive charge that it can form a bond with the lone pair of an oxygen or nitrogen or fluorine in another molecule. So that is hydrogen bond. Okay, so let's see the picture here. So the hydrogen here must, okay, let's see the words here first. The electronegative atom, oxygen or nitrogen or fluorine, have a stronger pull on the electrons in the covalent bond with hydrogen, causing the bond to be polarized. Okay, so this is one same molecule. This is the covalent bond actually. Covalent bond. The covalent bond is polar bond. So oxygen and nitrogen will, or even fluorine, will attract the electrons towards here and making these to be positive. So for hydrogen bonding to take place, the angle between the OH and H or even HF and the hydrogen bond is 180 degree. 180 degree, something like this. Okay, 180 degree, you can see they are horizontal. Okay, the number of hydrogen bonds depends on the number of hydrogen atom attached to oxygen or nitrogen in the molecule, the number of lone pair on the oxygen or nitrogen. Okay, so it depends on two factors. Okay, so for example, right, maybe you are thinking of let's say water molecule. Water molecule, it seems like there are, H2O, right? H2O, it seems to be, okay, let's say I draw out first. 2 lone pair, 2 hydrogen. This is one water molecule. So you may feel like, oh, this water molecule, they can form one hydrogen bond here with others. They can form one hydrogen bond here with others. They can form one hydrogen bond here with others and form one hydrogen bond here with others. So you may feel like, are they able to form so many hydrogen bonds? Actually, cannot also. They cannot form so many hydrogen bonds because of space problem. Okay, so if they form so many hydrogen bonds, they are like squeezed around, so not possible. Okay, not possible. So water can only form 2 hydrogen bonds per molecules. Okay, so we have to consider that also. So this is an example. Ammonia can form a maximum of 1 hydrogen bond per molecule. 1 hydrogen bond. Okay, so although you may feel like, oh, they have 1 lone pair, this one can form hydrogen bond, here can form, here also can form, here also can form. So are they able to form that many hydrogen bonds? So cannot. They cannot form that many of hydrogen bond because there is a condition here. It has to be 180 degree, you know. So these and these can form 180 degree. So these two cannot. So it has to be 180 degree. Okay. Now let's see more example. Okay. Yeah. Water can form a maximum of 2 hydrogen bonds per molecule. Although logically you feel like, oh, are they able to form 4? Cannot. They have to form 2. Okay, because of the 180 degree idea just now. So as you can see, 180 degree. So which is here? Lone pair, hydrogen, 180 degree. Okay, so here also lone pair, hydrogen, 180 degree. Okay, so 2 hydrogen bonds only. And because of that, because water can form hydrogen bonds, so water is something special. Okay, so what is so special about water? So first, hydrogen bonding in water causes it to have anomalous properties such as high melting and boiling points. So high melting points, maybe you feel like, is it high, 0 degrees Celsius and 100 degrees Celsius? It is kind of high compared to other simple covalent molecule where they are gas. They are not even liquid, you know, this is liquid. Okay, high surface tension where insect can stand on water, certain insect can stand on the water surface, and anomalous density of ice compared to water. So this is special because the solid form of H2O is less dense than liquid form of H2O. That is rare, right? So normally the solid form will sink, but this solid form will float on the liquid form. So it is anomalous properties. Okay, because of the hydrogen bonds. Okay, so of course there are explanation here. High melting and boiling points. Water has high melting and boiling points, which is caused by the strong intermolecular forces of hydrogen bonding between the molecules. In ice and water, the molecules are tightly held together by hydrogen bonds. A lot of energy is therefore required to break the water molecule apart and melt or boil them. Okay, so that's why that has high melting and boiling point, because of hydrogen bond. A lot of hydrogen bond to break. Okay, now let's see the picture here. So ice, you melt, this is water, you boil, then it becomes steam. You break all the hydrogen bonds. So the graph below compare the enthalpy of vaporizations, energy required to boil a substance of different hydrides. They purposely use hydrides Okay, so that it is fair in comparing, because H2O is also hydride, so it's hydrogen with something else. So hydrogen with oxygen, hydrogen with sulfur, hydrogen with selenium, hydrogen with this Te, selenium. Okay, so what we find is water has extremely high enthalpy change of vaporization. This is the energy to change liquid to gas. Okay, so um, basically, what are they comparing? These are actually the O, the S, and the Se, and the Te, right? So they are all group 16. Hydrogen with group 16, but this one has the greatest enthalpy change of vaporization because of hydrogen bonding. Okay. Now, the enthalpy change increase going from H2S to H2Te. Okay. You see increasing here due to the increased number of electrons in the group 16 elements. So all these are group 16, oxygen, sulfur, selenium, and thalenium. They are all group 16. But here they increase because of more electrons. So more electron means the instantaneous dipole induced dipole forces is getting stronger. This is the van der Waals forces. Van der Waals forces is getting stronger. So as the molecules become larger, so this one, the increase is due to the stronger van der Waals forces, or the stronger instantaneous dipole induced dipole forces. But here to here, the increase is due to the presence of hydrogen bonds. So based on this, H2O would have a much lower enthalpy change. Okay, so if we base on this, right, we should predict this should be somewhere here, right? But at the end it's up there, So what happened? Hydrogen bonds. However, the enthalpy change of vaporization is almost 3 times larger, which is caused by the hydrogen bonds present in water but not in the other hydrides. So this one no hydrogen bonds, but this one hydrogen bonds.